All right, good morning, everybody. So last time we were talking about NMR. Particularly, we were talking about proton NMR. Tell me what you know about NMR. What information can we get from NMR? What kind of bunch of stuff? Be specific. The what? What's that? Locations. What do you mean by that? What kind of information do we get from NMR? Pardon? We can get the quantity, the relative number of hydrogens through what part of the NMR gives us the relative number of hydrogens? The peaks? Now, depends on what you mean by the relative number of hydrogens. Are you talking about the signals or are you talking about the actual number of protons? The unique environments or the number of protons? Okay, so the unique environments are by the number of signals that we have. That's right. So in this particular case, we have 3 unique signals, meaning we have 3 unique proton environments. We also get the integration, which tells us the relative number of protons, right? What other kinds of information do we get? All those signals look like they're split into different things. What's that tell us? Does it? Okay, so the location, or where they're at on the shift, right, tells us their hybridization, and also, or what they're attached to, et cetera, et cetera. Aubrey, what were you talking about?
The number of the actual peaks in the little set.
The splitting.
Neighboring places are there.
That's right. Neighboring places are there. What do we mean? What do you mean by that?
Hydrogens that are like.
Okay. So if that peak that we see right there at just a little around 1.85 or whatever, there's 6 peaks in that signal. What does that tell us?
There's 6 protons not attached that are adjacent to it.
Not 6.
Sorry.
What's the rule? N+1. That's right. It's the N+1 rule for first order spectra, which is all we're going to be dealing with in this class. The scale goes from 0 to about 10 to 12 or something like that for proton NMR. This peak at 0, which is called TMS, is what? It's added to the solvent, but it in of itself is not the solvent. That's right. That's right. It calibrates the spectrum to 0. It is, by definition, given a chemical shift of 0. If we're moving further to the left, what do we call that? Downfield. And if we move further to the right, what would make a signal shift further downfield? Okay, so if we have a carbon with hydrogens on it, and if that's attached to an oxygen, it's going to appear further downfield. If it has halogens, it's going to appear further downfield. When you start to interpret an NMR spectrum, where do you start? Where do you draw the line? At 5. Everything to the right of 5 is what? SP3 or SP, and everything to the left? SP2, unless you get really far out, and then it's like carboxylic acids, and those are SP2 hybridized in a way. But okay, so we can get a lot of information. That's the take-home message, right? So let's use this now, and let's look at some examples. So let's look at iodo-propane, 2-iodo-propane. Will everybody agree with the environments that are listed there? Are these the same? And is this different? Okay, so we should see 2 signals, right? What would the splitting be for this CH3? We've got 3 protons, but what's its splitting going to be? How many neighbors do those 3 protons have? So we're going to have a doublet, right? What are we going to have for this single hydrogen here for B?
7.
Yeah. And so if we look at all of these, you can see what we're looking at here. So let's see if this makes sense. So we have this peak at about 4.3-ish, right? And that's going to be B. Does it make sense that it's at that chemical shift? Because it's on the carbon, yeah, right? So how many peaks do we see there? Do we see the right number? There's 1, 2, 3, 4, 5, 6, 7. Okay, so we've got 7 splits in this signal. That's consistent with the structure.
So we count the little teeny tiny.
That counts.
Okay.
Yep.
There we go.
And then we have a doublet here at about 1.9, which is consistent with these methyl groups. Now, if we look at the integration, does the integration make sense? You got to just kind of eyeball it. So the height of this line versus the height of that line. What should the ratio be? 1 to 6. Is that about what we got? More or less. If I look at that, there's about 6 of those in there. Now, if we look at 1,1-dichloroethane, again, we're going to have 2 environments, just like we had 2 environments here. The ratio is clearly going to be different, right? But notice what's happened to this peak at B. What's kind of unique about it? It's way down. It's past, it's really darn close to 6, right? About 5.9. That kind of violates that rule that I told you about drawing a line at 5, right? Why is that? Okay, there's 2 electronegative atoms attached to it, so it's going to pull it further downfield. But it doesn't change the hybridization, right? It's still sp3 hybridized. So that rule of 5 is just a rule of thumb. It is not the law. Okay, that's the thing that you need to keep in mind here. It is just a rule of thumb. It is not the law. So we have a peak there, and what's it split into? And what do we call that? It is a quartet, okay? And that makes sense because it's got 3 neighbors. This methyl group, okay, notice it's even pulled down a little further, right? It's past 2, whereas this one was before 2. Does that make sense? Yeah, because there's more electronegative atoms that are going to help pull that down as well, even though they're not directly attached. They're still in the molecule, and we see a doublet. So that's all consistent, and then we should see a ratio of 1 to 3. That's about 3 times the size of that, so it works out pretty well. Now, if we look at molecule, whatever this is, molecule 3, okay, 1,3-dichloropropane, we predict we should see 2 signals. That's in fact what we see, right? And B is going to be around what? Where's B going to be? Which one's B? 7. This one right here, about 3,7, right? And is it the right splitting? Yep, it's got 2 neighbors. And then A has how many neighbors? And so it should have how many peaks in there? And is it right? 1, 2, 3, 4, 5. In fact, we see it correctly. And it should be a 2-to-1 ratio. And I would argue that that's about twice as high as that, right? Because you got 4 protons for B and only 2 protons for A, so that's a 2-to-1 ratio. And that's in fact what we see. Okay? So draw those in. All right. Explain this spectrum for me. Does it make sense? We draw a line at 5. These are not past 5. These are just blow-ups of the insets. They're called insets. So here we have 5. Everything's over here. That makes sense, right? Should we see only 3 signals? Yep. All 3 of these signals are unique, right? And so we have C, which is pretty far downfield. Why is it so far downfield? And what's so electron withdrawing about that? Why should NO2 be such a strong electron withdrawing group? I mean, it's appearing at about 4.5 almost. There are oxygens. Oxygens are electronegative. Draw out on a piece of paper, draw out what the Lewis structure is for a nitro group, NO2. Just put a carbon and then NO2. Draw out the Lewis structure. How do I draw it? How do I put a nitrogen with two oxygens on it? Double bond. Where? Can it be both? Can't be both. Why can't it be both? Octet, right? But I can do this. What's the formal charge on nitrogen with 4 bonds? That's why it's so electron withdrawing. You have a formal positive charge on the nitrogen that's bound to that carbon. So it's going to appear pretty far downfield. Okay? And it has, this is proton C. How many neighbors do they have? 2, so they appear as a triplet. A, this methyl group is around 1. How many neighbors do they have? So they appear as a triplet. And then B, right, it's going to be kind of in between because it's closer to the nitro group than the methyl group, but it's further away than the methylene directly attached to the nitro group. So it's going to be somewhere in between. It comes just a little bit after 1, or after 2, excuse me. And how many neighbors does it have? So it should be 1, 2, 3, 4, 5, 6. 6 peaks. Okay, so this spectrum is very consistent with the structure that you see here. Okay. Now, why is it that we see these splittings? What is it about those neighbors that make a difference? Protons, we mentioned, right? The nucleus is stationary or it's spinning? It's spinning, and that makes them a magnet, right? So if you think about it, if we have a signal, okay, just from a single hydrogen, okay, you should just see a single line if all it felt was the magnetic field of the NMR spectrometer. It can either be spinning up or spinning down, right? That's all it can do. And so we're going to get one signal. However, if that hydrogen has neighbors, let's say it has a single neighbor next to it, meaning it will appear as a doublet, right? What really is that proton feeling? It's not just feeling B0. It's also feeling the magnetic field of its neighbor. And its neighbor can either be spinning up or down, right? And so if we think about it, that's what we would see in the absence of neighbors, because all it's feeling is B0. But if it has a neighbor, it'll feel the magnetic field of the NMR spectrometer plus the magnetic field of the neighbor that's spinning along with B0, but it'll also feel the magnetic field of its neighbor that is spinning down. And these are different. And so they'll appear at different chemical shifts. So it's one signal, but it's split into 2 because it's feeling the magnetic influence of its neighbor. Okay? This is an extremely weak interaction, but we have instruments that are sensitive enough to detect it. And that's cool, because now we get all kinds of information. Not only do we get the number of hydrogens that the molecule has through integration and chemical shift, but we also know what's next to it. And that gives us a lot of pieces in how to put the puzzle together. Think about how you put together a 1,000-piece puzzle. You don't just look at the individual pieces. You look at how they fit to their neighbors, right? And that's exactly what's going on here. Okay? You can use those splittings to tell, I know that's a signal. I know from the integration it's 1 proton, and it's split into 6, so it's got to have 5 neighboring protons. Well, how do you get 5 neighboring protons? CH3 and a CH2, right? So you know how these pieces start to go together. Okay? The difference between these 2 peaks is called a coupling constant. We abbreviate that as J. Fortunately, in this class, you're not going to need to use coupling constants too much. But when you take a higher level NMR spectroscopy course, these become very, very important, okay? Because they are constant. They tell you how the protons are actually interacting with each other. You can tell whether or not, by looking at coupling constants, whether or not protons are cis to one another or trans to one another. That's a lot of information, okay? So if you look at an alkene, for example, you can have hydrogens that are cis to one another or trans, and it turns out that the trans protons always have a larger coupling constant than the cis. So by looking at an NMR of an alkene, if you made an alkene in the lab, I could tell you, but just by looking at the NMR and the coupling constant, whether or not it's a trans or a cis. And that's hard to get that kind of information out of IR. It's hard to get that kind of information out of boiling point. It's hard to get that kind of information out of melting point. But I can get it really quick and in like 5 minutes from a simple NMR experiment. Okay? Now, if you think about why in the world would a signal be split into a triplet? It's because how many neighbors do we have for a triplet? We have 2 neighbors, right? So it can feel the magnetic field when both the neighbors are spinning in the same direction, or in the opposite direction, or as a mixture of both. This is exactly why you see a triplet. A real triplet is a 1 to 2 to 1 ratio. And it's because of the statistics of how the neighboring protons spin. Okay? It's statistical mechanics, it's physics. The physicists found this out long before the chemists ever did, but the chemists are the one that took this technique and exploited the heck out of it. Okay? Physicists really didn't know what they had at the time. Okay? It's really not that particularly interesting to them overall. But for us, this is really great information because most organic molecules, or all organic molecules I should say, have at least some hydrogen, right? So we can use hydrogen NMR to determine an awful lot of stuff. Okay? And so you can go through and actually do the combinations for a quartet. I'm not going to hold you responsible for that, but what I am going to hold you responsible for is why we see splitting. And we see splitting because of the neighboring protons and how they can either align or unalign with the magnetic field of the spectrometer. Okay? So let's look at some concepts tests. This came directly from the ACS study guide. And so you can expect things like this on the ACS exam. How many sets of protons would be observed in the proton NMR spectrum for this compound? In other words, how many signals are you going to see? How many unique environments are there? Huh? You count 6? And you are correct. And where do we get 6? Okay, so you're saying we'll see 2 unique hydrogen signals here, 2 unique hydrogen signals here, and then 2 here. How 2? Are these going to be identical, or are these going to be identical? You're shaking your head yes, and you're right. Now tell me why. Well, that's true, but what's the symmetry element? You're right, but you're just not using the right word. What goes through here? A mirror plane of symmetry, that's right. And so these protons are related to one another by symmetry, but this proton to this is not related by symmetry. So this will be a signal, and this will be a signal. Now let's go through real quick and let's draw what we think the NMR spectrum might look like. So the NMR spectrum is going to go from 0 to about 10, right? I'm going to draw a line at 5. And where am I going to see signals? Well, let's not talk about the splitting yet. On just what I've got here, am I going to see signals on both the left and right-hand side of the spectrum? Yes. Okay. So this CH3, where should it appear? Around 1. Okay. And what will its splitting be? So somewhere around 1, we're going to have a triplet. Okay. What about the CH2 that's attached to it? Where's it going to appear? It's going to be a little bit further down. It's attached to, those hydrogens are attached to a carbon that's what we would call benzylic or adjacent to an sp2 hybridized carbon. So where are those going to appear in our chemical shift table? Downfield from 1. Give me kind of a rough range. Okay, and what will the splitting be? Quartet. And I'm not drawing to scale, so about 2.5. Now, how about the CH2 that's attached to the oxygen? Where's it going to be? 3-ish, 3.5? Put it right here. What's it going to be? And now we've got the CH3 there on the right-hand side. What's it going to appear as? Just to the left of the 1, and it's going to appear as a what? Whoop. And I need to make it a little more to scale. There we go. Okay. Where are the aromatic protons going to appear? To the left of 5. How far to the left of 5? Okay, let's say somewhere around 7. How are they going to appear?
Well, the one with the mirror plane on the left is going to be further upfield than the one on the right.
Okay, so how are they going to appear? Is it just going to be a single line? Pardon? Yep, we're going to have a doublet. We're going to have a doublet and a doublet. One's going to be further upfield than the other. We're not going to get into why that is at the moment, but okay, so this is going to be one signal, and this is going to be one signal. This hydrogen has one neighbor, so it's going to appear as a doublet. This hydrogen has one neighbor, so it's going to appear as a doublet, and that's why we get a pair of doublets. But one of them is on the side with a more electronegative group, which should pull further downfield, and the other one has a group that is more electropositive, so it's going to be more upfield. And that's why you have this upfield-downfield shift around 7. Okay? Notice it's symmetrical, if you think about it right at 7, as it should be, because it's a symmetrical molecule. Okay? So you'll need to be able to look at a molecule and predict the spectrum, and look at a spectrum and predict the molecule. Okay? Both things are good techniques for you to have. And you'll do more of what we're doing right now in the lab than you will in the class, but because it takes a little bit more time. Which structure is consistent with this NMR spectrum? What should we do the very first thing? Count the signals. How many signals do we have? Can we eliminate anything based on that? We can eliminate C. Why can we eliminate C? How many signals does it have? 4. It should have 4 signals, right? A CH3, a CH2, the other CH2, and the other CH3. Those are 4 unique signals. Can't be that spectrum, right? Doesn't work out. So, okay? Can we eliminate any others based on that information? No. Everything else would have 3 signals. Let's look at A. Is A consistent with that spectrum? The CH3 on the left is going to be what kind of signal? How many neighbors does it have? So it's going to be a singlet. The CH2 has how many neighbors? 3, so it's going to be a, and the other CH3 has a, should be a triplet. So it looks like I got a singlet, a quartet, and a triplet. Is that consistent with the spectrum? I got a quartet, a singlet, and a triplet up there. I do. That's 4 peaks, that's 1 peak, and that's 3 peaks. It's consistent with the splitting, but is it consistent with where they're located?
So when you're looking at like B, that's only 3 signals because the CH3, CH2O is the same on each side.
That's right, it's symmetrical.
And so that's why it counts as 1 instead of counting as like CH2 and CH3.
Correct. If we look at this, what do we notice about the quartet? Further downfield or further upfield than the methyl, or than the singlet? This is downfield, meaning that the quartet should be on a what? Electronegative atom, right? Here, this is the only thing that can give me the quartet, right? And it's just connected to carbons. Whereas this is the only thing that can give me the singlet, and it's connected to a oxygen. So if A is the correct answer, these should be swapped. So that's not consistent. Okay? How about B? What would the splitting be for this? A triplet. What would the splitting be for this? Quartet. And what would the splitting be for this? Singlet. That's consistent. Is this consistent with the location? Yeah, the singlet here, not attached to anything electronegative. Here it is. That seems to make sense. So this is definitely a possibility. How about this one? Yeah, so nothing here should be this far down, right? So we've eliminated C based on the number of signals. We eliminated A based on the relative locations. And we eliminated D on the same grounds. So B is the only logical choice here. Okay? So we identified signals. We identified where they were at. And we worked our way through it that way. Okay? Believe me, it gets easier with practice. This week is the NMR in lab, right? Yeah. All right, let's do a little more NMR practice. Some of these are a little hard to see without the light on, so try not to go to sleep. All right. So when we're elucidating a structure by the use of proton NMR, there are these four things that we talked about, right? Keep these four things in mind and go through them. Number one, determine the number of signals. That tells us the number of unique environments. Two, determine the chemical shift. That tells me what type of hydrogen I have. Is it a hydrogen attached to an sp3, an sp, or an sp2 hybridized carbon? Is it attached to something that's more electronegative? I can get a lot of information there by where the chemical shift is. Look at the integration. That tells us the relative number of hydrogens that are contributing to that signal. The relative number, okay? And then you look at the splitting patterns, and that tells us the information on the number of neighboring hydrogens that we have. Okay? If we look at this molecule, this is a simple molecule. It's a styrene derivative. Okay? And again, this is a calculated spectrum that I did on a computer, and it just didn't transfer very well. So how many signals do we see? We see 1, 2, 3, 4, 5, 6. Does that make sense? Tell me how that makes sense. 1, 2, 3, 4, 5. Can't count. Sure you can't count? What would help here? What would help Aubrey here? The way I've got it drawn, this is just a CH2, right? But we really need to draw it like this. Right? These two protons are not identical. Why are they not identical? So this proton is cis to a methyl group, but trans to an aromatic ring. This hydrogen is, so are these identical? They are not. And so we have 1, 2, 3, 4, 5, 6 unique environments. Why are these equivalent? Yeah, if I take this and I turn it, you'll see that there's a mirror plane through the aromatic ring. Model building helps here, okay? And you can see that. And so we should see 6 environments. 1, 2, 3, 4, 5, 6. This one right here, what does it belong to? It is the methyl group. It's in the right location. It's about 2.5 because it's attached to an sp2 hybridized carbon, so it's going to pull it down a little bit. These two right here just past 5, or which ones? These two, and one of them is cis to the aromatic ring, one of them is trans. Don't worry so much about that. And then we have 3 signals here, right? 1, 2, and 3. And you can look at the splitting pattern if it was a better picture and you could determine which ones were which, okay? Let's look at one that may be a little more challenging for you. Which of these structures is consistent with this proton NMR spectrum?
That one before that one peak?
That's a good question. That's why this is a little more challenging. What do you think? Does that look like one peak that we've talked about? Or does that kind of look like 2 that just happen to be really close? They are 2 separate signals that are really close to one another. So how many do we see? We see 4 because we ignore the one at 0, right? Can we eliminate anything based on that information alone? Can't eliminate just based on the number of signals. Okay? So now we got to go through and really do some work, right? So we've looked at the unique environments. What's the next thing that we do? Now we look at the chemical shift, right? So is there anything that's way far downfield? Yeah. We've got some stuff that's pretty far down, right? Just, straddling 4. Can we eliminate anything based on that? We can eliminate A?
Because none of the hydrogens that are close to either electronegative atoms are going to have. Well, never mind. Should be a doublet.
What should be a doublet? Because these 2 hydrogens only have one neighbor? Do we have that? No. Okay, so we can eliminate that. I'll take a 1 in 3 chance over a 1 in 4 chance any day. That's not bad. Anything else we can eliminate?
We can eliminate P. There would be 2 P's that far down.
So this would be a triplet downfield, right?
There wouldn't be anything else up.
Okay. So now we're at a 50-50 odd. Even better. I'll take it. What do you think?
That peak right before a triplet.
What does it look like to you? It looks like a peak and then a taller peak and then a peak, right? That looks like a triplet. And this one looks more like a quartet. So it looks like we should have a quartet that's a little further downfield than a triplet. Okay, so C is the correct answer. Okay? Listen to me. You're not going to be able to look at these NMRs and it just come to you. This is a process. Okay? You don't want to live with a 1 in 4 chance. Go through the process. Use the techniques and eliminate. Okay? Eliminate the things that make absolutely no sense. And then if time gets to be a crunch, then you've got odds on your side, okay? But if you look at this, this makes perfect sense. This CH3 is going to be the furthest upfield because it's the furthest away from any electronegative atom, and that's what we see, just a little bit past 1, and it's going to be a triplet because it's got 2 neighbors. These 2 hydrogens are going to give me a signal that's going to appear as a quartet because of their 3 nearest neighbors, and it's connected directly to an oxygen. It's going to be pretty far downfield. So there we go. Here we're going to have a triplet, and here we're going to have a triplet. So we have 2 triplets, right? Which one is this one? This is the one just under 3, and this one is the one just under 4. All that data comes together to tell us what we have as a structure. Oh, excuse me. How many signals? We've got 5. Okay. So, can we eliminate anything based on that? One, two, three, 4, 5, 6. It would indeed.
Does this ring always put off 3 signals?
What ring? The aromatic ring? Not always. It depends on what's attached to it. Here we would get 3 signals because there's a proton here, here, and here, right? So that's 3 environments. But here we're not going to have 3 environments, for example. We're just going to have 2 environments. But here we're going to have 1, 2, 3, 4 environments. What about B? What can we use to eliminate B? That would be a singlet that would be somewhere around here, right? Do we see it? Not there. So y'all have eliminated A, we've eliminated B, and now we can eliminate D. How? Too many signals. The answer is C. Okay? Now, anytime you have a substituent on an aromatic ring, or 2 substituents, excuse me, that are in a 1-4 relationship, we call that para-substituted, and we'll learn more about that later. But when you have a benzene ring that is substituted like this, you're always going to see this pair of doublets around 7. Always. And so when I looked at this, I knew it had to either be B or C based on that information alone.
See, you got that cetyl bonded O single bonded to H over there,
Which is,
that little peak at the end.
yep, that's an aldehyde. So if you look at this, right, we've got 4 hydrogens on this ring. Will you agree with that? And if you look at it, I've got a mirror plane that runs through here. But I don't have a mirror plane that runs through here, do I? So that means that this hydrogen and this hydrogen are identical. And this hydrogen and this hydrogen are identical. That's why I have 2 signals. When I look here, I have no mirror symmetry at all that's going to relate any of those signals on the aromatic ring. So I've got to have 1, 2, 3, 4 signals. Now, they may be really close, but I'm going to have 4 signals. Here, I've got a 1-4 relationship as well, so I'm going to have 2 signals that are going to appear as doublets. And here, there's a mirror plane that runs through here, but there's a hydrogen here, right? So I'm going to have 1, 2, and 3. Does that make sense? Okay. Notice above it, you get 1H, 2H, 1H, and 6H. What is that? It's the integration. They're telling you what the integrals are. Okay? It does?
Wouldn't that CH3 and other CH3 be the same thing?
They are.
So it would only have 3 peaks.
So I'd have 1, 2, 3.
Oh, okay, got it.
Mhm.
So the hydrogen don't oxygen doesn't. All right.
What about A? How many signals should it have? How? All the CH3s are identical, and then the OH, right, or the hydrogen on OH, so it should have 2. So this one is nonsense. How about B? I'd have 1, 2, 3, 4, 5. How about D? Based on counting my signals, it's C. All I had to do is be able to count to 4, right? So that's pretty good. Now let's go back and look at it. So these methyl groups give 6 protons. They're identical. That also told me something really quick, right? And they're doublets. Because how many neighbors do they have? 1. This single proton right here has how many neighbors?
8.
So it's going to appear as this multiplet. And in fact, this peak is so tiny it's hard to see. But 1, 2, 3, 4, 5, 6, 7, 8, 9. They're there, right? And then we have these 2 protons, which are here, which appear as a doublet because of the nearest neighbor. And then this single hydrogen appears because of this OH. Now, it turns out very important, something that we didn't spend a whole lot of time talking about. It's very difficult to get hydrogens that are on heteroatoms to couple with their neighbors. That's why this appears as a singlet. You would think it should appear as a triplet because it's got 2 nearest neighbors. In fact, you can get it to appear as a triplet if you're really good at your NMR. But it turns out that these things exchange off due to hydrogen bonding, and usually you see them as a singlet. So usually NHs and OHs will appear as a singlet and not coupled to their nearest neighbors. That's why this only appears as a doublet for these 2. Okay? Now, having said that, I can go into the lab and I can show you how these all actually will couple, but you have to use a lot of care in how you prepare the sample to make that happen. Okay? But for the purposes of this class, usually OHs and NHs do not couple to their nearest neighbors. All right, we're going to get started in on carbon NMR. Now, it turns out that carbon NMR is not as abundant. It's less sensitive. So I can go to the NMR spectrometer and I can get an NMR spectrum, a proton NMR spectrum in 5 minutes. It takes me at least a half hour to get a good carbon spectrum because proton is 99% of hydrogen, right? Carbon-13 is only a little over 1%. Okay, so the amount of carbon-13 that you have is a lot less. So it's a little more difficult to do. But carbon-13 is NMR active, and we can get NMRs. Okay. Now it turns out, same kind of analysis. The number of resonance tells us how many unique carbons we have in a structure. The splitting will tell us how many hydrogens are attached to that carbon. However, we quite frequently run this in what's called proton decoupled spectra, where all you see is single lines. We'll talk a little bit more about that. The chemical shift reflects the hybridization of the carbon, just like for proton. We get sp, sp3, sp2. Okay? And the chemical shift also tells us something about the electronic environment. In other words, if a carbon is bound to an oxygen, guess what? It appears further downfield. If it's attached to another carbon, it appears further upfield. Okay? And very important in NMR, getting integrations is very, very difficult. So we rarely integrate a carbon-13 spectrum. So you can't tell me that because a peak has a higher integral that there's actually more carbon there than a carbon signal that's actually of lower intensity. Okay? Yes, there are techniques to do that, but it's more difficult to do. Okay? So for the purposes of this class, do not try to integrate the carbon signal. Okay? Carbon NMR is spread out over a much larger range. Don't let that scare you. Proton goes from 0 to about 10 to 12. Carbon goes from 0 to about 200, 220 ppm. This is actually in your favor because carbon spectra get split out from one another further. It's easier to count the signals. In proton NMR, remember that one where we had those two things really close to 4? They were kind of hard. Is that a triplet? Is that a quartet? We were making those arguments. In carbon, they usually get spaced out by several parts per million, and so you can see them quite easily. Where would you draw the line here? At 100. Everything to the right of 100 is going to be SP hybridized carbons, which are going to appear around 80, or SP3. And everything to the left is going to be SP2. So by looking at a carbon spectra, if you see stuff to the left of 100, you know you've got SP2 hybridized carbons, right? If you see stuff to the right, you know you've either got SP or SP3 hybridized carbons. It's still, I mean, it's still a little bit of a rule of thumb. But since this is a lot broader, it's a lot more concrete than for proton, okay? So yeah, that's where we're going to put our line, okay? Now in your book, you've got approximate carbon shifts. You will not need this kind of detailed information for my exam. You will need it for lab. So make sure you take your chemical shift tables with you, okay? This is typically how we see a carbon-13 spectrum. This is in the so-called proton decoupled mode. You don't see splitting. Everything appears as a single peak. I like this a lot better. Notice how many environments we have. 1, 2, 3, 4, 5, 6. This is diethyl phthalate. We have 6 unique environments. Okay? For those of you in polymer science, this is something that you'll see in your spectra as a contaminant sometimes, because phthalates are used to plasticize certain things. So if you ever, if your solvent ever comes into contact with a rubber bulb or a piece of rubber tubing, you usually get this as a contaminant in your spectrum, okay, because the solvent will pull this stuff out, okay? But if you look at it, it makes sense where these are, and these are just single peaks. 2 is a tiny peak, okay? But notice there's just as much 2 as there is 3 and 4, but the peaks are very different in size. That's why you can't trust integrations. You can't go, oh, there's very little number 2 in there, right? Well, number 2, yeah. But anyway, diethyl phthalate. That's the structure. Now, we can run that in proton-coupled mode, where the protons actually split the carbon signals, and this is what it looks like. 5 appears as a triplet because how many hydrogens are attached to it? 2. 2 plus 1 is 3. 6 appears as a quartet because there are 3 hydrogens attached to it. Okay?
So now it's only when it's on the carbon, it's only the one attached to the carbon.
That's right. Not adjacent. Because carbon-13 can't split carbon-13. Can anybody tell me why? In a natural sample. I shouldn't say that. In a natural sample, why doesn't carbon-13 split carbon-13 if they're adjacent to one another? What's the odds of having 2 carbon-13s directly attached to one another if they're only 1% abundant? Essentially 0, right? And so you don't have carbon-13 splitting carbon-13 under normal conditions. We're going to pick up with this on Wednesday. We've also got a demo during Wednesday, so come prepared for that. But if you would, take out a piece of paper and put your name on it and turn it in up here at the front, please. You can print if you don't have a good signature.